Okay, good morning everyone. Very happy to have all of you here as part of the School Connect. So, why did I call you over? Well, it just turned out all of you were from Chennai. So, I thought, okay, I can as well do this session in person so that you can also have better interaction, understand this a little more, in detail. Most importantly, the reason I sort of called you over is to give you a feel for what to expect in this program. Okay, because the first week you started doing C programming and you might think, well, what is the electronics in this? Why are we doing programming straight away, right? So I thought it is important that I give you a trailer of what to expect over the coming months, right? And also throughout this electronic systems program. Okay, so the idea was, what can I introduce you to, right, in terms of electronics. Okay, so we live in an era where there is an electronic gadget on us or around us at any point of time, wherever you are. This is true. So then I thought, okay, what better way to introduce you to electronics other than demystifying the mobile phone itself, right? So today, you do everything on your mobile phone. So why don't we dive a little deeper and understand how this happens at a very high level? Okay, the theory, to understand all this, you will need to do courses, you will need to do all that. That is what the movie is. This is the trailer, just to tell you very quickly what is happening. At least you will see so many fight scenes, you will see so many songs. That feel you should get. Okay, that's the idea of this, session here. Okay, so let me start with, I've kept some things here. What is this? Yeah, handy camera, right? Maybe 2000, 2010 and all videos, every wedding you would see somebody like this, especially if they come back from the US, they would have one handy cam like this, and they're shooting videos and stuff like that. Unfortunately, all they did was to shoot videos in weddings. Okay, and what is this? Digital camera. So this came in around 2010 or something like that. I bought this in 2012. Okay, some 13 megapixel camera, 21x optical zoom and stuff like that, right? What is this? Huh? What is this? I need to know from the younger generation. I know my generation will know this. Yeah, huh?
Mobile phone, like a phone which can be carried around non-stop to one place.
Yeah. So essentially, this is a cordless phone, is what. Yeah, we used to call it a cordless phone. Okay, but why am I showing you all this? Why is this related to what we are going to talk about?
All these things are stuffed inside.
So all these things are now available in your mobile phone, right? Wherever you go, you take a selfie with your mobile, you shoot videos with your mobile and stuff like that, right? So how did this magic happen, right? You just look at the size of this camera. You look at the size of this camera, size of this phone, right? And forget the landline part. Just look at the size of this phone. How did this magically become a, something that can be held in your hand, the size of your palm, essentially, right? So that is where the miniaturization of electronics actually has a role to play. Okay, this is basically in the field of VLSI, they call this the Moore's law. Okay, every 2 years the transistors would scale by a factor of 2, and then they became smaller and smaller and smaller and smaller, and effectively you landed up with a gadget that was, this also is quite big actually, but which could do all that this is doing and much more. Okay, so the idea is for us to today understand how some of these things happen. Okay, so first of all, just to start with, this thing, right? I'm going to pass around just one screw from this mobile phone for you to just see and appreciate what size you are talking about. Okay, you're talking about some really small sizes, which is maybe a couple of 100 strands of your hair or something like that. Okay, that's how small it is. So can you just collect this and pass it around? Just pass be careful about that screw. It is that small. Okay, these screws are not available in your regular hardware shop. You need special screwdrivers to be able to, like, unscrew them, screw them back and stuff. But effectively, that's how small it is. Okay, so we'll talk more about the miniaturization and stuff like that, but let's get into the basic idea of a phone. What is a phone used for? What did you want it for? Communication, right? So what do you mean communication? You're going to make a call to somebody, and what you speak here should be heard. You can also pass it there to the parents and all that. Just pass it on that side. So you want to be able to make a call, and you need to be able to send that message that you have said to the other end somewhere, right? This person could be sitting somewhere in the US, it could be anywhere, right? So what is the first step that has to happen if the mobile phone has to do something with your call and transmit something to the other end? What's the first step? Huh? Receiving signal, transmitting signal is all happens much farther down the line. The first thing is, I have said something, it is in the air. How does that go into the mobile phone? How does the mobile even capture that information for it to package it and send it across to the other end? So it has to, like he said, it has to first take in that information that is being said, right? And put it into my mobile phone or a computer and stuff like that. So what do you think does this job for you? Microphone, right? So the first thing that you need in any electronic system is a sensor, because some things that you do in the real world are not directly available as electrical signals for you to process and start changing and altering. So in order to get these real world energy, take the real world energy from one form to another form, is what is known as a transducer. Transducer does this job for you. Microphone is a transducer that basically converts your sound energy to electrical energy. Okay, it will go into your computer as either a current or a voltage, and then you can process it, and then you can start doing many interesting things with it. Okay, so what I'll first do is I'll give you a feel for what does this this sound wave even look when we speak. Okay, so this is something you guys know. It's a standard headset. I've just plugged it into this computer, and what I'm going to do is I'm going to record this on a sound editing software called Audacity. Okay, so what I'll do is I'll just do a record first. Check. So can you hear me? This is a test recording. Okay, so what you see here is that when you speak, the sound energy, which is basically longitudinal waves, right? I think you would have studied this in your 11th standard, that these are longitudinal waves. What are longitudinal waves? Yeah, but what is the primary characteristic of this longitudinal wave? The direction of energy flow is the same as the vibration of the molecule. So the air molecule, so as I speak, each molecule is vibrating back and forth. Neighboring molecule is also vibrating back and forth, and all of these are executing simple harmonic motion in a certain phase, right? And that leads to a wave, right? That's what you call a sound wave, a longitudinal wave, right? So there is this microphone which basically takes this sound wave that reacts to this energy that is being produced, and it causes some vibration that changes something internally. It could be a capacitance, it could be anything. Let's not get into those details for now. It could change a capacitance, and thereby you can see a change in the electric characteristics of the output. It could be a voltage or a current here. So what you see here is, when I speak, I see some waveform like thing that is happening here, right? And I can zoom in a lot into this region. Yeah, so you see that as I speak here, this is what happens. Okay, now I'll just delete this. Let me also, yeah, check, 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 check. I speak louder, it results in an increase in amplitude, right? I speak softer, it results in a decrease in the amplitude, right? So the wave is being modulated by what is being said, and the volume of my speech is actually controlling the amplitude of that signal, right? Here it's a voltage that we are talking about. Okay, now let us see what happens to other component of a wave, which basically is the frequency. How do I alter the frequency? What is frequency, by the way? Yeah, so it's number of oscillations per second, right? If you have a periodic oscillation, in 1 second, how many oscillations do you have, right? So that's the idea. Anyway, so how do I now change the frequency? Were you able to see any frequency content in this speech of mine? So what is the frequency? So let us look at that. Okay, I'll do one recording now where I'm going to speak in a very bass voice. Okay, and let me blow this up. Okay, you see something like this, right? Now let me add another track. Okay, I'm going to mute this, and on this track I'm going to do something slightly different. I'm going to speak in a very high frequency, high pitched voice. Okay, I know that wasn't great, but so what you see here, right, you see a certain oscillation in that case, right, and here you will see a much faster oscillation that is happening. That is, the number of oscillations per second have now gone up. So when you speak, your amplitude is controlled by the volume of your speech, but the frequency is controlled by what kind of vocal cord you have. So women generally have slightly higher frequencies, the men have slightly lower frequencies. Okay, but in any case, the typical audio range that we are talking about is 20 hertz to 20 kilohertz, right? Beyond that we cannot hear anything, right? Beyond that, bats and dogs can maybe hear, but we cannot hear anything. So if you are looking at the audio signal that is going in, right, it is going to be at most 20 hertz to 20 kilohertz. In fact, it is only these instruments which actually generate frequencies which are close to 10 kilohertz and all that, like the snare in your drum, that psh, if you hit, that will give you a very high frequency. But normal instruments will typically operate in 300 hertz, 400 hertz, somewhere there. Even the female voice, which is high frequency, will not be of the order of 10 kilohertz. It will go slightly higher to the hundreds of hertz kind of thing. But there is also something known as harmonics. Okay, harmonics is basically integral multiples of your fundamental frequency, right? So there is not only that frequency that I showed you, but there is also some harmonics. So because of that, typically we will be talking about 4 kilohertz to 5 kilohertz. At most, the voice content that we are generating needs to be only that much of frequency range. Okay, and therefore you don't have to even worry about going all the way to 20 kilohertz, right? So that's why these mobile phones and other things, they would have optimized a lot of these things for the voice. Okay, so in Zoom and all that, you would have, sometimes you would have seen an option of optimize for voice. So if you're doing music and all over Zoom, it will sound very bad. Why? Because those frequencies are getting cut out, right? So if you can optimize for the voice, and that's what they have done in the mobile phone, because that's what you're doing most of the time. You're not going to send some high quality music through a call, okay, right? So what you do now is, you have, taken this voice of yours, the mic has converted it to some sort of an electrical signal with some frequency content, okay. Now I need to send this across. Where am I going to send it? To the, but the receiver is sitting in America, no? You are making an international call.
CPU, the CPU or like it's mobile equivalent.
Yeah. So no. So I'm saying from the phone, now the voice goes in, the phone does something to it, and then has to send the signal out somewhere, right? So first of all, what does it send it? What can it send it with?
Radio waves.
Electromagnetic waves using an antenna, right? Electromagnetic waves, by the way, are transverse waves. That is, the direction of oscillation is now going to be perpendicular to the direction in which the energy flows. The longitudinal waves were vibrating like this, and the sound also moved like that. Electromagnetic waves, the electric field will vibrate up and down, magnetic field will go right and left, but the energy will go forward, okay. Anyway, so an antenna has to, now where does it send it? Right. So these are a lot of these terms you have heard, okay. I am just trying to put all of them in perspective for you today, okay. So wireless communication means you are now trying to send this wirelessly to the nearest tower, okay. Why is it called cellular phone? Because there are some cells that each tower can cater to, and you will basically move from one cell to another cell, essentially. That's why it was called cellular phone, and that's why they can also track you by saying you are within this range of this tower. That means you are within this, because they know, right, you are communicating to this tower. If the tower is closest here, there is a certain range in which my antenna can send out signals. That will not be very large. So I cannot talk to a tower in Mumbai. So they know I am in Chennai. Not only that, I am in somewhere near Adaya, because I am communicating with this tower here, right? So that wireless signal will be sent to the tower, and then it goes to some base station and all that. But the important part is, once you reach that tower, you don't have to do wireless communication anymore, because those towers are not moving. You understand? So you get the signal, you process it, and then you do high speed optical fiber communication or something like that. You could even do satellite communication if needed in some places. If you are remote, you are not able to lay those cables and all that, then you do any form of communication which is going to work, because wired communication is always more reliable than wireless communication. You would have seen that, right? Your landlines are absolutely, even in rain or flood or whatever it is, this will work, because the cables went underground somewhere, they are shielded nicely, safe, they simply will work, okay. So therefore, they employ wired communication out there. So it will go through that wired communication, then it may go through satellite, whatever, go to the other receiver's tower, and then that tower will again wirelessly transmit back to this receiver's mobile phone, okay. That's the signal path that I am talking about, okay. Now let us say that I have a wire from here to your house, I have a wire from here to your house. I want to send two signals, okay. I want to send two secret signals. What can I do? I will just send it on both of them, right? Will there be any problem? Let's say I want to send like a telegraph code, right? I want to send ... right? I can send it to him, I can send it to him. The two messages can be completely different, and they are not going to interfere with each other. Can I do the same thing in wireless communication? Why?
Since it's wired communication, it cannot go anywhere, but due to signals, it may.
Okay, good. So you're sort of getting there, but anyway. So where else have you seen wireless communication? Where else have you seen this? Outside the mobile phone. Even before the mobile phone. Actually, this mobile phone, what is?
Submarines with
Yeah, submarines.
underwater, you can't really have wires. Right?
Yeah, submarines, maybe walkie-talkie of a policeman. But where else? Something that has been around for decades on end.
Television.
Television is one, right? You have through some satellite something you get TV and all. But even more common, radio. Radio. You all listen to radio, correct? Now, what is your favorite radio channel? 92.7 what? No, FM, alright. Now, see this very interesting thing, okay? A sine wave has three things: amplitude, phase and frequency. I showed you that, right? You can control amplitude, you can control frequency. Phase is sort of, where it starts. So, don't worry about that. They did not characterize this base station, the radio station, as 1 volt amplitude. They did not characterize with phase, 45 degrees off. They seem to characterize it uniquely with frequency, 192.7 megahertz. So, somehow one number called 92.7 has uniquely characterized a radio station. Okay, we need to understand the reason for this. What is this 92.7? It's a frequency number, that's okay. But is it in the radio station, is it a number of a room that is sitting there? What is it?
The frequency of the signals being transmitted from there.
Okay, now what do you hear in the radio? Eventually, yeah, news or whatever, or songs. What did I tell you the audio range was? 20 hertz to 20 kilohertz. Where did megahertz come in? 92.7 megahertz. Mega is 1000 times kilo, correct? So, some number has magically come in there, and not only that, it seems to uniquely characterize that radio station. In a sense, it's indicating that if you are doing 92.7, I cannot do 92.7. Why is that?
Because then the two signals will interfere with each other.
Exactly. I told you that if I had a wire to his house, wire to your house, these two signals don't interfere with each other. Therefore, I didn't have to do anything about it. I could just send it freely. Both of you could receive it without any problem. Now, if I want to send the same, I want to do the same thing in a wireless medium, I have two messages, M1 of T, M2 of T, which are not the same, and I want to send it to both your house. I cannot send it wirelessly like that, because even if you are very close, by the way, don't think about antenna, attenuation, not that. Even if you are very close, from here to there, from there, I cannot send the same message to both of you, because they interfere with each other. I have X of T, X1 of T, which I want to send to you, X2 of T, which I want to send to you. They will just become some X1 of T plus X2 of T in the air. My antenna sends to his thing, X1 of T, it radiates in all directions. The other antenna also does the same thing. Effectively, what will be in this air is X1 of T plus X2 of T. Okay, so that is why you need to do something very, very specifically to uniquely put these guys on certain frequencies so that they don't interfere with each other. So, today if you want to fly a drone, can you just fly a drone like that on your own? What should you do?
We need a remote control set.
No, remote control set, okay. You need to get permission. Why?
Because the radiation from your control set to the drone does not interfere with any other.
So you need to buy and own that particular frequency band. Only then you are guaranteed you will talk in your band, you are not going to interfere with another person's band, right? So that's why, of course, in Tamil Nadu there is this 2G spectrum that all of us would have heard of, right? So essentially what was that? Essentially people were buying spectrum in the frequency space. Okay, and so they basically said, okay, for radios, FM would be this much. AM or amplitude modulation is another way you can do the same thing, which happens at lower frequencies, kilohertz. Okay, for a certain reason. FM happens at some megahertz. Mobile communication all happens at the gigahertz range. So what you do, you take this audio signal, which is frequency content, and then you have to modulate this signal with a carrier frequency. That carrier frequency is what is that 92.7 megahertz. Okay, you modulate it and move it from, so let's say all of us are speaking, all of us are occupying 20 hertz to let's say 2 kilohertz. All our voices are in that range, right? But I am now going to move one person's thing to 0.4 gigahertz, another person's message to 2.5 gigahertz. So between 2.4 and 2.5 gigahertz, how much space do I have? 0.1 gigahertz. 0.1 gigahertz is 100 megahertz. This is 100,000 kilohertz. So there is so much of space between those two carrier frequencies for me to accommodate any amount of voice signal that I want actually, right? So very safely without any interference, I can even do it with this 0.1 gigahertz difference, right? So now what I do, I will transmit both of them at 2.4, 2.5 or whatever it is. Other person there, okay, the person who's receiving it, right, which is, who's the receiver? The base station is going to receive it at this sort of frequency, right? In the case of the radio, you were receiving it at home. So what did you do? You tuned your radio to 92.7 and exactly at 92.7, you would start receiving that signal. Because you know they are sending at 92.7, you need to look in the air for that particular carrier range. And then you do what is known as demodulation of that signal. The process of taking the voice signal and moving it to higher carrier frequencies is called modulation, bringing it back from there to the original voice. Because if I play that megahertz signal to you, you will not hear anything. It's nothing because you cannot hear it, right? You have to bring it back to that same kilohertz range that you are talking about, and then other person can hear it. That is called demodulation. Okay, so this is just a, don't worry about these terms. Okay, you need to keep in mind why you needed to do this modulation, essentially to keep these signals apart, right? So that is sort of the interesting signal chain of the mobile communication part, right? Now what I'll do is I will now send across some of these things, right? This is a part which so this is the mobile phone, okay, and I think this was somewhere here, if I remember right, okay, somewhere, or no, I think it was here. Yeah, it was like this, okay. So what do you think this is? Yeah, mic or speaker, right? So a speaker typically has a magnet, okay. So what you do is you modulate that, change the current around magnet, and that will cause different kinds of vibrations, which is what leads to producing these sound waves. So typically if it has a magnet, it should attract the screw. So just a very simple test to say, okay, if I thought this was a speaker, and typically it will have a magnet, well it does. And there is also another speaker, because when I keep this phone like this and talk, I will hear from here for the calls, but my music and all will play out of this guy, right? That you would have seen. Sometimes you will hear like this, right? So there are two speakers and stuff like that. So I will pass this around. Please, you can take a look again just take a look at how small these speakers are, right? How they have, nicely arranged it and stuff like that. It is I would say a very amazing thing that has happened, right? It's reached a point where electronics has become like magic, right? People just think that magic is happening when you see these things, right? But it's not, we don't want students to think like that. That's why we are doing these kind of sessions to demystify these things for you. Okay. Anyway, likewise, what do you think this is? What is it? Camera, right? So this has been shrunk to this, okay, but it's important to note that I cannot say that this is equivalent to this, because this is a 21x optical zoom. The bulkiness of this camera does not come from the electronics, it comes from the optics. Inside there is a chip, there is an IC which does all the processing, which is again so small actually, okay. So we must be very careful about just saying that, oh, it's all the same, it's all equal. No, you cannot do bird photography with these kind of mobiles, right? You need lenses, you need big lenses. For that you need the cameras. But again, for going and shooting videos in weddings and taking selfies, this is enough. You don't need this thing. So that is where they have nicely optimized. Like how I said, for the voice signal, they have optimized all their communication part. Likewise, for the video part also, there are some very simple things that we do, and therefore, just pass it around there, okay. So, it has been optimized nicely for the kind of videos and cameras that, but nevertheless, it is quite amazing that the cameras today are extremely powerful in mobile phones, as even the front cameras, not just the back cameras, right. So, it's amazing. Some of them have like 4 cameras, and you take all these images, process it, and give you the thing, okay. Anyway, so you can think a little later, I'll pass it around again, but if you take all these individual components, just look at the size, sent you the speaker, sent you all that, right, the camera and all that. If I just put all these parts one beside the other, see, look at all these wires and all that, right. If you look at it, this is the connector, okay, this is the connector. Now there is some long wire that is just extending it for some reason, but if I take all the electronic components and just put them one beside the other, right, it will probably come to the size of matchbox. Just assemble it one beside, tile it one beside the other, you can accommodate this in a matchbox. Why is the mobile so big then? Battery. So this has a bigger screen, which is okay, but then you also have a watch, Today people have a watch, right? Smart watches that they are able to do. So it's not that the screen needs to be that big also, but fundamentally what determines the size of the mobile is the battery. That's why what you see is, in this iPhone, they would have placed the battery here, right, and you see it's almost the length of the phone, right, that's exactly what will fit here. And what they did was they simply assembled the components around the battery. Everything has been now fit around that battery, right. You take a bigger mobile phone, I have a bigger battery, because it has a bigger screen, it has a bigger processor, whatever stuff like that, right. So the battery is a very, very critical component of this mobile phone, simply because it is a finite energy source. What does finite energy mean? It means that this battery can store only certain amount of charge, okay. You cannot have more charge than that, and if you run out of charge, you will lose the battery, you have to recharge. So you would like the battery to last for 6 hours, 8 hours at least, right, or preferably 12 to 14 hours also, depending on your usage, right. So the key point is that in the mobile, right, you have to be very careful about every picojoule, every femtojoule of energy that is being spent on any activity. It's not like the desktop. See, the desktop is connected to a power supply. As long as there is power, there is infinite energy available for me to do whatever I want. I don't need to optimize every femtojoule of, I can be a little lax, though it's still not advisable from a design perspective, but that's how we design. You design for what is needed. You don't over design, because otherwise the cost of your desktop will shoot up, right? They cannot afford that in a mobile phone because it's a finite energy source. Okay. So now I will do one interesting experiment for you here. Let me call Shivagami. Okay, I'm going to call her. Don't pick up. What do you notice on my mobile?
The screen was black.
Ah, why?
Because it won't use up energy on like display because you're not going to see it anyways.
Correct. Exactly. Right. So somebody inside there is keeping track of all the small things that you are doing. Are you going near? That's why they put a sensor there. You keep your hand also, it will work. It doesn't have to be the ear. You just do this, see this thing blank out actually. Okay, so I can show you that also. It's not, they don't look for your ear. That's what I'm trying to say. That's all, right? They just look for whether you're blocking it or not. And most likely, if you are blocking it, you are probably on a call, right? Unless you choose to like keep this and like, okay, that's your problem, right? But they do very smart, simple things. Common sense works, right? Now, who does this? Huh? No, you need a sensor. First, you need a, like I told you, any physical action in the real world needs to be translated to some electrical signal. Only then the mobile or any device can do something about it. That sensor has to be there. So, there has to be a sensor which says, okay, light is gone or something like that, right?
Something like mobile processing unit.
Okay, so inside this mobile phone, apart from all your communication related stuff, you know, the antenna, right, the mic, speaker and all that, there is something very fundamental setting called a microprocessor. There is a microprocessor, just like there is a microprocessor in this desktop, and this mobile phone of mine is probably more powerful than the desktop I owned when I was in my college, right? Way more powerful than that, right? So, what is a microprocessor?
It's like a small chip,
Hmm.
silicon chip.
Right? It's a chip, yeah, but what does it do? What can it do? Huh? So, okay. So, the sensor converts those inputs and gives you some electrical signal. A microprocessor is supposed to act on it. It is supposed to see, oh, the light has gone, it means it's near the ear, I need to turn off the display. That's what it has to do, right? So, how does the microprocessor do all this?
It's connect.
Hmm.
For example, if the light is blocked out, then it will access the memory for its scenario. Memory will return a value saying to shut off the display and it will.
Yeah. Okay. So interesting. So he has brought about another term there, right? There's a microprocessor, there is a memory. Okay. Microprocessor and memory have to act together, right? What is a memory? It basically just stores data. You give an address, you will get the data. Okay. You give an address, it will give you the data. That's what a memory does, right? And it stores, you have to store it in binary form, digital form. Again, don't get into those details, forget all those things, right? Just a address versus value map. You give an address, you will get a value. That's all the memory does. What does the microprocessor do? The microprocessor actually does not know what to do. It has no idea what has to be done. Okay. So, I am going to demonstrate this using some nice this thing. So, let's try this demo, okay, and I would like two of you to come forward, okay. So, you are going to play the role of a microprocessor,
Okay.
Okay, so you keep these two things with you. I'll tell you what these are.
Okay.
That in one hand and this in one hand. So come here. Yeah, come here, come here. I know. Don't worry. Okay, now so what am I doing? I have things like this written. A1. On the other side, I have a number. Okay. Similarly, I have something called A2 and I have another number. Like that, B1, B2, I have 4 sort of things. Okay. Now, actually, one second. Yeah. I need one more person here actually. Come. Or we'll have the girl. Wait. Come. Two boys are already here. Come. Okay. So just be here. You can come here. Okay. Come here. Come. You stand in front of me. It's okay. Now there are certain things which I have kept here. Okay. This is the microprocessor. Okay. It has no idea what to do. It has absolutely no idea what to do. Okay. Now you have to lift this thing and there is something written. Okay, on this. Okay, so you just lift the first one and tell me what it is.
Move A1.
Move A1. Okay, A1 is that address. So I have given you an address. You open that and tell the microprocessor what the data in A1 is. 35. Can you write 35 on that sheet? Put it back. Yeah. Okay. So this is done. Okay. Now the microprocessor again has got 35 with it, still has no idea what to do. Next one.
Move B2.
27. On the other sheet, write 27. Okay. It got 2 numbers now. Still it has no idea what to do with those numbers. Okay. So microprocessor in some sense is very dumb. You have to tell it everything that needs to be done. Right. Next one. Add those two and write the result on one of those sheets. You can keep this pen. You need it in some time. Okay. So what's 62? Next one. Okay.
Add A2.
No. So it add contents of A2. So this time I am not doing move A2 and then add. I am saying whatever is in A2 directly add. Okay. Take 2 and tell him the number. 41. Add 41 to that resultant number. Yeah. Okay. And keep that 62 also. Now, last one.
Copy to A1.
Copy to A1. Whatever you got finally there, you are writing it back to A1. Okay. So can you open A1? Just strike what is there and just write this number. Okay. Now, what you saw here is exactly what a microprocessor does. A microprocessor day in and day out does only one thing. It fetches an instruction from the memory. That's what he did. It's simply, so this is the instruction unit, which is simply fetching instruction after instruction after instruction from what is known as the program memory. This was a program memory in which we have programmed what needs to be done. Whether it is sensing, turning off the screen, all that can be now programmed into some code, right? And at the lowest level, it sits in such elementary instructions known as assembly instructions or machine level instructions, right? So the microprocessor, this microprocessor instructs the program instruction unit to go fetch from the program memory the first instruction. Then if that happens to be accessing the memory, it will get data from the memory. Then you get the next instruction. Maybe that also was accessing the memory. The third instruction is to add these two numbers. Add it. Fourth instruction, again something else. Finally, you write back the memory, right? But all this microprocessor is doing is telling this fellow, fetch, decode, execute. Fetch, you decode. What is fetching is just reading. Decoding is to understand. Move means move from here to there. Add means add. Subtract means subtract. That is what is the decoding part. Finally, you have to execute it. That is what he did. He actually did the addition, subtraction and all that, right? And wrote the numbers, but he will write it back to his own paper. So these are called local registers in a microprocessor. Microprocessor will write and deal only with these registers, access, process and send it back to the memory. This is what happens day in and day out. Okay. Thank you. Thank you all. Yeah, you can leave it here. Okay. So effectively what you can do with that now is to simply code whatever you want. Whatever you want, you can code in that. Okay. So who does this coding for you? I mean, who does all this management for you? It is essentially the operating system. Okay, there is an operating system that is sitting, okay, and it is sort of doing all these multiple tasks for you. Okay, interestingly, if you write a C program and you run it on the microprocessor, at the time when your C program is running, there is nothing else running on the processor. Nothing else runs on the processor. Right? You may think that, oh, I'm able to access 10 tabs. I'm able to access 100 applications in parallel. Right? It appears that all of them are running in parallel. No. At a time, there's only one app that is running in that processor. So how do they achieve that? How do you think they achieve that? At a time, you can run only one.
Maybe they store like the data from whatever we have previously separately in a temporary area, then like put it on pause basically. Once you're done with this, you can continue.
Yeah, sort of he's almost there. So this is what they call time multiplexing, right? So what is the frequency at which these processors operate? Have you seen any spec computer? What numbers have you seen? When you buy a computer, a desktop, what do you look for? What are the things you look for?
Processing speed.
What is the processing speed? What is the number you have typically seen? No, RAM processing speed. But what processing speed number? Typical number, what have you seen? Is it like 220 kilohertz, 40 kilohertz, 32 bits? That's fine. But this processor speed, that number, it is in gigahertz. You will see it as 2.4 gigahertz. That means the microprocessor in there is running at 2.4 gigahertz. Gigahertz is what? 10 power 9, right? Gigahertz corresponds to a nanosecond. Okay. The humans can only perceive such things. Such speeds you can perceive, milliseconds. At most microseconds. Processors are operating at nanoseconds, 1000 or 10 power, a million times faster than what we can perceive in reality. So the processor can actually do things one at a time, but at such speeds that you think everything is happening in parallel, because you are not able to perceive that difference. Right? Because we are limited by what we are able to perceive. We have evolved in a way as human beings to perceive such time, units. Nothing beyond that. And therefore, the processor is able to fool us by actually doing all this. Okay. So now, when I switch off my mobile and I start from scratch, right? All these programs are gone. Everything is gone. This is called a RAM, random access memory, right? What is random access memory, by the way? You can randomly access any location, right? If I have a stack of books without causing any damage, the only thing I can do is to take the top book and put it back. That's like a stack. That's not a random access. I can only access the top of the stack and then put it back. Always I access only top of stack. But random access is I can access any location. That's why I said A2, A1, B2, B2. I could tell her to access B2. You would get it. You know, that's what I mean by random access. However, these random access memories are volatile. That means you switch off power, everything is gone. That means whatever program you had, whatever instructions, this program, this code, all these things that you had programmed and kept will all go. So how does that come? That comes from what is known as non-volatile memory. Non-volatile memory means it will remain even after the power is off. That data will remain in non-volatile memory, and the first thing that happens is there is a small program written in non-volatile memory which says load the operating system. The first thing that the phone will do or a computer will do, right? You would have seen from a black screen, it will go to welcome to Windows, something it will go. How does that happen? It's basically doing booting. The boot code is going to say go and load the operating system from this location, and then you hand over control to the operating system. Then the operating system, when you choose to run a program or whatever, will hand over control to you. Do exactly all this. All the while, whether the operating system or your program or anything, microprocessor is only doing the same thing. Fetch, decode, execute in a loop. Whole day. Even now, that's all it is doing on the phone. Okay. So, with this aspect of, the microprocessor programming part, you can effectively do any control that you want. You have 4 cameras, you want to process the image and do something, you can do it because you have now the power of programming and this thing. So, that's why even if you are doing electronic systems, programming is a very integral and important part. Without programming, you cannot do anything in hardware today. In fact, today's hardware is so complex that you are not going to be able to control the hardware without appropriate software. So that's why in your program that we have started now, C programming is part of your first few courses that you need to understand. And C is also a very nice language that is simple, easy, and also generic enough to allow you to understand other languages in future, Python and other things, right? So the idea of, why I called you today, right? Like I said, I don't want you to think, oh, we are doing software, we are doing programming, we are not doing electronics. Well, no. It's a very critical part, as you would have seen today, and step by step, and of course, mathematics is a definitely integral part of electronics, right? Without maths, you cannot handle electronics. So that's a critical part. And after that, you will get into electronic systems thinking, where you will see some of the things that I showed you today, this mobile phone, this thing. There we will go into slightly more interesting theory also, right? What is meant by voltage, what is meant by current, what is a battery rating, right? Why is it rated that way? What is a charger? What does the rating of a charger mean? And all that you will see in the electronic systems thinking and circuits course in the first 4 weeks itself. Okay. So anyway, I am done with my demo. I am now open to any questions that you may have.
One thing regarding you said, like, for the phone, it will sense. If it senses light, then wouldn't if you're in dark room, wouldn't it automatically switch off?
No. So you are right. So it may not be light based.
Wouldn't it be like distance?
You are right. It might be. You're right. So it might not be light based. That's a very good catch. Yeah. So that's a very good point. So
also, like, shouldn't it be like when there is a call only? Because otherwise, if you just touch that area, it will.
Correct. So when there is a call, yes, of course, that again. So again, these are all taken care of by the programming, right? There's a call is being made, right? Some flag will be set, call is going on. So if that flag is on and there is a distance, something that you have sensed, then turn off the screen.
And gate.
Yeah, and gates, exactly. That's where logic design comes into picture. Precisely.
Like the operating system is used to manage the entire device, but then in order to like upload the code to the operating system, how is that done?
So that's what I said happens in the boot code. In boot code, there is a non-volatile memory which has a certain sequence of instructions that simply loads all this to the thing, right? So for example, these instructions were there right here. I said all of this is gone. It will be plain paper at the time of starting. But then that code says from that non-volatile memory, get all those instructions and populate this. And then it will hand over to the processor saying start executing from here. The operating system itself is a program. That's what I am trying to say. Like this, just like this. Somebody has written this program and kept it. You are loading that program onto this RAM and saying now execute from here. Yeah, any questions?
Will you practice breadboards?
Yes, in the electronic systems course, the second term, you will straight away get into breadboards, and so the lab is currently running for the students, and they are indeed doing breadboard experiments. So you'll be given a kit, an electronic kit, which you can sit at home and do all the experiments very nicely. Absolutely.
Then you go to
PCBs are we are still working that out, but the hope is you will get into something like that also.
when will the first lab session be?
Lab session will happen the second term, right? Actually, in the end of the first term, electronic systems thinking and circuits also has a small lab component. Okay, because we want you to get used to the kit. We want to make sure that you come here and you get trained on the kit before you go back home, right? And so that itself will have a small lab component, some first order filters and stuff like that you will do on the breadboard. So the breadboard will actually come right at the end of the first term itself. But main experiments you start doing in the second term. Yeah. Anything else? The parents, any questions that you may have also, please feel free to ask. Okay, so it is both similar and not similar. So the first of all, why we came up with this is the India is sort of getting into an interesting phase of electronic systems. You would have seen this announcement by our Honorable Prime Minister about the 3 semiconductor fabs and all that, right? So India is attempting to get into a certain, a new era of electronic systems. So that is going to open up a lot of job requirements in terms of skills, and the regular BTech program does not impart those skills. So that's why in this program, if you exit with a diploma also, you will get trained with a certain skill set. That doesn't exist in the BTech program. BTech program is you have to finish 4 years. After 4 years, you get a degree or you get nothing. Whereas here, it's more about skills, picking up skills all through, and equal theory and practice all through the program. So that's the main difference. BTech is very theory oriented. We are bringing in a lot of practical stuff. Yeah, lab term. Yeah. So just like the evaluation of your exams happen at exam centers, the evaluation of the lab will happen at IIT Madras. You come over at a designated slot, right? You can pick. It's not that we'll give you one date and say come on that date. You can pick amongst 2-3 dates. You come here and the evaluation will happen in person, but that's only once a term. You will be doing about 8 experiments from home, right? And you'll be uploading videos, we'll be correcting them. But final evaluation will happen when you are here in campus.
Sir, my mother had asked more about the campus recruitments.
Yeah. So campus recruitment, so the support that is given for campus recruitment is very similar to what we have for our BTechs here, right? Our BTech, we have a placement cell that will talk to companies, attract them, tell them about the program. So same kind of support is being given here also. That is already happening for the data science. People are already getting jobs. People are already, data science started in 2020. So that is already up and running in the data science. So the infrastructure is already there. Same support will be extended to the electronic systems program as well. But getting the job is ultimately your, dependent on your performance, your skill and all that stuff, right? Even to our BTech students, we cannot guarantee that everyone will get a job. They do. Eventually they do. But as IIT Madras, we cannot give that on paper. You have to do well and you have to, perform well in the interview. Job prospects are across like a spectrum, right? There is this, you can do PCB design, you can do, embedded systems design, you can do firmware, support, you can do the regular jobs that people get in the VLSI industry if you finish the 4-year degree, right? So it covers like a vast spectrum of electronics market. Okay, then thank you all for coming. I hope this session was informative, and we look forward to interacting with you over the next couple of months. Okay.